Hey everyone, my name's Eugene, and today I'm here to talk about tooling at Twitter. You may know me from my previous work on Scala Reflect, Scala Macros, Scala Meta, and most recently RSC, a new Scala compiler that we're developing at Twitter. The underlying theme behind all these projects is metaprogramming and tooling. So first I started doing metaprogramming for Scala at EPFL as part of my PhD thesis in Martin Anderski's lab. And now I'm representing Twitter as the tech lead of the Advanced Scala Tools team. Typically, I begin my slides with credits. And this talk is definitely no exception, because this whole internal initiative to build next generation tooling at Twitter was a huge collaborative effort. Core contributors to that effort were my team, in alphabetical order myself, Shane, and Uma, as well as our early adopters within Twitter. Again, in alphabetical order, build, CI, code review, the guys from our department, as well as library teams, CDL and CSL, and other folks at Twitter. Lots of people contributed to that. Slides are too small to fit everyone, but I'm really, really grateful to you guys. The last, but not the least, I would like to highlight our open source collaboration within Scala Meta, a metaprogramming library for Scala, which is cornerstone to the entire effort. So for the last 2 years, Scala Meta has been basically a two-man show. It's been myself and Olaf Gerson from the Scala Center who've been running the thing. And Olaf, if you don't know the guy, he's the author of Scala FMT, ScalaFix, a bunch of other tools, including Metals. And I would say our joint collaboration on Scala Meta has been super successful. It's a great open source success story. So despite working for different employers, having different internal roadmaps and oftentimes different opinions, we've always been able to come up with a joint roadmap that allowed us to achieve our internal goals, plus further the state of the art of tooling for the benefit of the entire community. So yay open source, and thanks to everyone who supports open source. All right, on that note, I would like to proceed with the talk. And in general, I'd like to keep this talk really grounded in practice. So we will start with a problem looking for a solution, not the other way around. And speaking of the problems, here's one. We have a huge code base. So pulling up the numbers from our last year's Scala Days talk, we literally have tens of millions of lines of code. And that's not counting auto-generated stuff. This code is organized in tens of thousands of so-called targets, which is like lightweight projects, units of compilation in the terminology of PANS, the build tool that we're using. And clearly, to be productive in a code base like this, we need smarter tools, something that we call semantic tools. So these tools, they need not only to look at the syntactic structure of the program and the text, but also be able to answer questions like, well, what does this identifier resolve to? Or, what's the type of the expression? Something that you typically expect from an IDE, but on a larger scale. I promised you a problem statement, and definitely this thing is not crisp enough. So we went ahead, we prioritized user asks, and we ended up with the following list. It's somewhat arbitrary, but hey, we're doing tools for our users, so we have to take this stuff into account. Well, first of all, we would want code browsing to understand the structure of the programs. That is, it would be desirable that we'd be able to open our source code. In any tool, really, we have a lot of flexibility. And then at least be able to follow hyperlinks, like, command click, control click in your IDE, something like that. Of course, the more smart functionality, the better, but this is like, the basics. We also want similar things for code review. So if we are doing a code review, it would be desirable to be able to go to definitions. And finally, it would be great to run code rewrites against our entire code base. One of the benefits of the monorepo, this huge repository of code that we have, is that we can evolve everything simultaneously. So it would be great to take advantage of that. And clearly for languages like Scala, just regex-based rewrites, they're not enough. Otherwise, how do you figure out that something .get actually refers to option.get, for instance, and not to other method called get? Well, anyway, as I said, I'd like to keep this talk grounded in practice, which means that, well, let's see whether we have solutions that work out of the box. That would definitely be the most economical way to deliver what our users want. But it turns out that since this is Scala, it's basically nightmare mode, not even hard mode. Just to go back to the times when we were considering this effort, code browsing for Scala was limited to IDEs. But unfortunately, given the humongous size of our code base, no IDEs could load it in its entirety. So that's definitely workable because you can export part of the projects and then load that part into IntelliJ. But clearly, this is suboptimal for navigation purposes, something that I mentioned before. Speaking of code review, at Twitter, we're using Fabricator. And even though Fabricator has some support for semantic features, for Python and PHP, there's something out of the box. It does not have Scala integration. Remember, nightmare mode, right? And for code evolution, there was this thing, still is, called Scala refactoring, which was used for code rewrites in Enzyme and Scala IDE. But unfortunately, at that point, it had a backlog of fundamental issues and no maintainer, which was kind of sad. And finally, there were some proprietary solutions with different levels of Scala support, but internally we've been burned by unsuccessful experience with one of them, which is why we decided to go with something else. So all this stuff, all this background, it increasingly pointed to the fact that we would need custom development. And therefore, some folks, myself included, argued for creating a dedicated team for that purpose. And ultimately, that happened in June last year, and we founded a team with the mission to go boldly where no man has gone before, meaning to improve the state-of-the-art of Scala tooling, both internally and then also to open source the most important of our efforts to benefit the community. And the roadmap, it basically mirrors the problem statement that we've seen in previous slides, to improve code browsing, code review, and code evolution. OK, so how do you go about building semantic tools? Well, a good idea would be to take existing semantic APIs, something that compilers are good at, and just use them out of the box. So back then, when we were considering this project of improving our tools, there were basically three choices: compiler internals light, aka Scala Reflect, and compiler internals extra light, aka Scala signatures. So that's definitely lots of code, which has been battle tested for over a decade. That's pretty solid. But unfortunately, when we considered it, we decided to go with something else because of the following reasons. The first problem that we found with Scala C internals is the learning curve. So as I mentioned before, the compiler is more than 10 years old, and it accumulated lots of stuff. Basically dozens of modules, thousands of methods, and the data model, to tell the truth, it's quite complicated. So just to give you guys a mind bender, right? So we have objects in Scala, right? Object definitions. And so in the Scala compiler, objects are modeled not just by one entity, but by two entities. A module symbol, so module is a Scala C lingo for object, and a module class. So that's fun. And as a result, we have two ways to refer to a type of an object. Something called a this type for a module class symbol, or a singleton type for a module symbol. And the most amazing thing is that only one of those ways to refer to the type of the object is valid in one context, and another way is valid in another context. So this is pretty mind-blowing, and I mentioned that I did PhD in this area, but believe it or not, I had to rehearse this part before this talk yesterday, so that to make sure I get this right. So yeah, it's that hard. Anyway, the second blocker that we found is insufficient documentation. So Scala is a pretty involved language. There's lots of ways to define things, lots of different types, and syntactic variation is also pretty impressive. So to make sense of all of that, to see how it all plays together, we definitely need more than just Scala docs. So even though in Scala Reflect, which became the foundation of the current Scala macros, we did lots of work on documentation, it still wasn't enough. And so if we were to use compiler internals, I would be exposing the team, myself included, to these kind of mind benders that I mentioned before, which is kind of suboptimal. Well, if we're talking like really practice-oriented stuff, these problems, number one, the learning curve, and number 2, documentation, if we squint at them, there are success stories here, right? So clearly people in Martin's lab at EPFL, people at Lightband who are maintaining the Scala compiler, they have figured everything out, and they've been productive delivering new functionality. So this is, you could say this is a social problem, right? But anyway, we found out a really hard technical blocker here, and this is why we couldn't use compiler internals at all, unfortunately. So the thing is that compiler internals require a compiler instance. Well, duh, right? But the thing is, the compiler has been optimized over more than a decade, or I would say overtrained towards the batch compilation use case. So speaking of batch compilation, how does this work, right? You give the compiler lots of sources, and you don't expect it to finish very quickly because, well, it's Scala, it does a lot of work, lots of features. So you wait until it's done, and then you inspect the results. But unfortunately, this means that many of the use cases that we were targeting, for instance, find all references, they were basically prohibitively slow. So let's say we want to find references to a certain definition in our code base. How do we do that with the Scala compiler? Well, we give it the entire Twitter source, which is millions of lines of code. We wait until it type checks stuff. If it has enough RAM, and if it has enough CPU time, which is days, guys. And afterwards, we traverse the result. So clearly, this is unacceptable, which is why we had to give this up. And unfortunately, tools that use the Scala compiler internals, like say Enzyme or Scala ID, they have the same problems. And they either roll their own infrastructure, for example, for indexing, or they just give up and accept the limitations. So that's the story with the Scala C API. And to be complete, to make sure that we are not reinventing the wheel, we definitely looked into the developments in Dotty. So even though Dotty hasn't been released yet, still we needed to try everything to avoid custom development because, well, custom development is super expensive, right? So let's go through a brief overview. Since you guys are sitting here, you probably attended the keynote that Martin gave yesterday. And you know that Dotty is going to become the new Scala compiler, sometimes in, well, about 2 years, if I recall the slides correctly. And there is a dedicated meta programming API in Dotty. Something's shaping up. And since Scala Reflect is based on Scala compiler internals, it was discarded because it's incompatible with Dotty compiler internals. So, long story short, meet Taystee, which is a serialization format for Dotty compiler internals. And currently, it's used in Dotty IDE, as well as the upcoming macro system. There was an awesome demo that Martin gave yesterday. So guys, if you're watching this in video, please take a look. That was really impressive. And yeah, so let's take a look again. As I mentioned before, we're willing to use really bleeding edge software as long as it solves our problems. So before doing this talk, yesterday when I was preparing, I went ahead, cloned the master of LAMP PFL Dotty, and just took a look. It looks like the API for Taystee lives in the Dotty library in the file called taystee.scala, but it's arranged in a bit unusual way. So let me comment. So instead of having case classes to model the language, the API lives in an enclosing class called Taystee. And those data structures, they're encoded in abstract types, extractors, as well as these class tags. So something that we extensively explored in Scala Reflect days. So back then in Scala Reflect, why we did that? Because we needed basically one-to-one correspondence with compiler internals. So thanks to that, we don't need to define any data structures. We just piggyback using the cake pattern on what the compiler has. However, in the implementation of Taystee in Dotty, there is an abstraction layer between compiler internals and the API. This is a really great improvement. Unfortunately, some details of compiler internals, they still leak. So for instance, these module classes that I mentioned before, some other stuff, they're still there. But never mind that. Let's take a look how to use Taystee. So what I did, I just did a text search over the Dotty library and looked for methods or something that returns Taystee. So it looks like there's just one occurrence like that in the trait called universe. So universe looks like it's a wrapper for something called Taystee, and the context, I won't go into details. But the thing is that, again, let's see what instantiates this universe. And in the Dotty library, again, there's just one usage, which is a stub. So that's curious. Now, if we expand the search scope to the entire Dotty code base, we finally find an implementation, which is called compilation universe, and it lives in the compiler source code. So basically, this is the only thing that implements Taystee right now. And in a way, it's similar to the situation with Scala Reflect, where the compiler was basically the only implementation of its metaprogramming API. So just to sum it up, what we've gleaned from Dotty master, it looks like Taystee is similar to Scala Reflect at this point, but re-implemented for Dotty. So remember these blockers that were arising for our project when we tried to use the Scala Reflect, and they still apply. So Taystee is still based on compiler internals. It's a bit underdocumented, but the main technical blocker really is that it requires a compiler instance. We definitely need to keep in mind that this is pre-release software. As I said before, the release date is like 2 years in the future, roughly, according to the official talks. Lots of things may change. However, for our project, what was relevant is that our customers need semantic tools right now, or even better, yesterday. So we had to do something. So we had to roll our own semantic APIs. As I mentioned at the beginning of the talk, we did this work as part of Scala Meta, which is an open source metaprogramming library for Scala that we started like 5 years ago during my time at EPFL. Back then, it was just syntactic APIs, so just a parser and some other stuff. But the characteristic thing about Scala Meta is that it's focused on tool writers, as opposed on what the compiler exposes. And it turns out that this niche was quite useful. And 5 years later, Scala Meta is like an umbrella project, an organization that accumulates more than 10 projects that add up to more than 10,000 commits by more than 200 open source contributors. And because of the strategic importance of this initiative, both Twitter and Scala Center fund full-time developers who work on Scala Meta and related projects. So now, how we solved this particular problem at hand, semantic tools, right? Towards that end, we designed something called Semantic DB, which is a data model for semantic information about programs in Scala and other languages. For instance, we support Java. The data model does, and our code generators do partially. And the key thing, just like Scala Meta, Semantic DB is focused on what tool writers need from the compiler, not what's convenient to expose, like it was in Scala Reflect, for instance. And this is a super tricky business, right? Because what do tool writers need? How do we figure this out? Because once we have a compiler, we can just expose its stuff, and it's easy. But here, it's a bit of a different problem statement. And as a result, this required collaboration between a compiler expert, myself, I did a PhD on that stuff, and a tool expert, Olaf, the guy who I mentioned before, who works at the Scala Center. So let's see what we've come up with. Here on the slide, you see a protobuf instantiation of a central data structure in our model called text document. Text document contains semantic information about a source file, so to speak. So source file can be specified via either a URI or its text, just embedded the source code. In addition to those attributes, text document contains some more, like the version of the schema, for instance, Semantic DB v3, which is the current version, and the language, which would be Scala or Java. And the most important, the most interesting thing for tool writers definitely happened in something called sections. So those symbols, occurrences, which host parts of the symbol table, compiler messages, and so on and so forth. Let's take a quick example and try to obtain a Semantic DB payload for a hello world program. So here we have an object with the usual main method and the print line, nothing else. To get to Semantic DBs, we need to use our compiler plugin for Scala C. And so we just invoke Scala C as usual, but pass in the compiler plugin as well. And in addition to that way, we also expose a CLI tool, which ships together with Scala Meta that wraps this process. So that you can say meta c test.scala. It says the same as Scala C test.scala, but for Scala Meta. After either of those invocations have been completed, we see additional files in addition to class files, right? And so for every Scala file that was in the project, you will have a Semantic DB file, like test.scala.semanticdb here, in a special meta.inf folder. If we try to just cat the file or XXD, we will see that it's kind of a mix of binary stuff and symbols. So it's weird. But that's all right because it's encoded in protobuf, and protobuf is a binary format. So as I mentioned before, we provide CLI tools in our distribution. And there is a tool to take a look at those semantic DB payloads called Metabeam. It's like Java P or Scala P. P stands for printer. If we inspect this particular file or this particular directory, which is why I said metap dot, so then it traverses everything, we see the attributes. So as I mentioned, semantic DB v3, the URI is just test.scala, as well as the sections. So let's take a look. It's where the most interesting stuff happens. So the symbols section, it's like a symbol table in the compiler. What it does, for every definition in the file that we've been compiling, it stores its signature, various metadata about it, like flags, for instance, final for object. So the signature, it includes base classes and declarations. We can see that for object test. For methods, it's the entire parameters, parameter types, and return type thing, and so on and so forth. So that's symbols. Now let's take a look at occurrences. What occurrences do, for every identifier in the program that we've been compiling, like object test, def main, args, so on and so forth, we have its range, zero-based, which is why test is on line 0, as well as a symbol, which you can treat as a unique identifier of the definition that the identifier refers to. So we can see, for instance, that an array of string, that's part of the standard signature for a main method, it points to a Scala array and Scala predef string. And printline, it's basically the first overload of printline in the predef object. So stuff like that, you can probably already see how it's useful for go-to-definition or find all references. Now, this was just a glimpse, so we definitely don't have time to go into details in this talk, but luckily Olaf, the co-author of this entire thing, he gave a talk earlier this year at ScalaSphere in Krakow. So just check out the thing for details. It has many more and much better examples for semantic DB payloads, as well as the introduction to the CLI utilities. So just MetaC and MetaP, it's not everything. Also, an overview of tools which are based on semantic DB. So quite a good talk. Please take a look if you want an introduction to this entire API. But now we will move on. Since our problem statement was about improving the developer workflow with semantic tools, let's see how semantic DB helps with that. To begin the discussion, to see some examples, I'd like to piggyback on open source tools that Olaf hacked up, together with the community of open source contributors. So there's MetaDoc, Metals, and ScalaFix. And it looks like I have enough time to just show you guys some live demos. Let's hope the internet works. And we will start with MetaDoc, which is something that was created by Olaf and also Jonas Fonseca and some other open source contributors. On the Scala Meta website, we have this sneaky URL, just scalameta.org/MetaDoc, which shows the web application. So as you can see, this is some sort of an editor. Well, it's not really an editor, it's read-only. But it's kind of a pretty thing. So what's that? How do we get to that? MetaDoc is a CLI tool, which takes semantic DBs and source code, and then produces this static website. So this website is powered by something called Burmako, which is a crucial component of VS Code, which is basically something that supports LSP, Language Server Protocol, but in the browser. So long story short, without getting into too many technical details, we can see that there's some functionality available here that you expect from IDEs and that we wanted to achieve. So for instance, find all references. You do that and see how fast it is, so basically instantaneous. That's because there are indices in memory. And it's not because it's regexes. So really, if you have chunk stream in your comments, something like this, it wouldn't be shown here. Now, how has semantic DB been able to help us to build this tool? There are multiple answers. Well, first of all, semantic DB is really independent of compilers, which means that this MetaDoc thing, it only needs semantic DB files. It does not need a running compiler. As a result, you just produce those files, you store them somewhere. We don't care. Just give us to them. Give these files to us. And secondly, an interesting thing about Scala Meta, and it's kind of a good thing about having a simple data model, no cake patterns, no nothing, is that this thing trivially cross-compiles to Scala.js or Scala Native. So in this case, this thing is running in a browser, and a Scala.js program, it can use Semantic DB bindings, protobuf bindings, to load Semantic DB payloads right here, which I think is pretty amazing. When Olaf first showed it to me, I was like, whoa, Olaf, what did you do? Oh my God. So that's quite neat. And you can see this is a great experiment that partially solves the code browsing problem. Awesome. Now, on to the next cool thing, which is called Metals for Scala Meta language server. Metals is another project that's part of the Scala Meta organization. It's an effort, again, an open source effort, and major contributions were done by Olaf, Gabriele Petronella, and Alexei Alekhin. Very interesting work, guys. And now I'm just going to show some slides that Olaf prepared for one of his talks. So you should really watch Olaf's talks. It's quite amazing what he pulls off. Let's see whether I can remember the URL. Yes. That was good. I cleaned the browser history in order to not be embarrassed by everything that would show up. And now I had to remember this URL. Oh my God, it's just, wow. So anyway, Metals is the foundation for an IDE. It's an implementation of something that's called the Language Server Protocol. And it's based on Semantic DB as well as other technologies to achieve IDE experience. It's a work in progress. So basically, you should not be using it right now, but it's growing steadily. Right now, I'm just going to show some of the features that are available in Metals. So first of all, Metals is integrated with ScalaFix, another tool that I'll be covering before. ScalaFix uses Semantic DB to power semantic refactorings. So in ScalaFix, you can write custom rules where you ask, hey, Semantic DB, what's the symbol for this get thing? So is this an option.get, something that I mentioned before, or is something else? And thanks to the integration, because Metals is based on Semantic DB, ScalaFix is based on Semantic DB, these guys are able to pass these payloads around, achieving smooth integration between tools. Another thing is also something powered by ScalaFix. You can have something called code actions in LSP. So basically here we communicate with ScalaFix, and it goes back to the editor and returns a diff so that you can do things like remove unused imports. Also powered by Semantic DB. There's lots of stuff, for instance, integration with Scala FMT, and I invite you guys to take a closer look later after the talk. But just to sum it up, how Semantic DB has been useful in this particular case. Thanks to Semantic DB, it's possible to accumulate multiple sources of information about programs. The incomplete information that the compiler has about what you're typing, about half-broken code, the stuff from the class path, something that's called indexing in IntelliJ, and it all goes into the same data schema, which allows for really easy indexing, regardless of wherever the semantic information comes from. OK, so back to the slides. Now I just need to have this thing disappear. Please do. Oh, no. This is disheartening. OK, I think now this thing should go away forever. Yes. Anyway, finally, ScalaFix, something that I mentioned before. This is a linting and refactoring tool developed by Olaf and open source contributors. This is Olaf's project at the Scala Center. And thanks to Semantic DB, here we can write custom rewrites that use information about code. For instance, members, types of expressions, to do, well, whatever you want, whatever code evolution you would like to implement. Now, this was a good showcase of the power of Semantic DB. Thanks to the fact that Semantic DB has a simple schema, it can be immediately useful. You don't need a running compiler. You just need protobuf bindings, and this is it. And thanks to the fact that you don't need a running compiler, you can also index stuff and make semantic information available very, very quickly, which is critical not just for projects that have millions of lines of code, like our code base, But also for medium-sized projects, even if you have 10K lines of code, how do you do find all references with the Scala compiler? This is an unclear problem. So some of these tools, some of these open source tools that we're using internally. And also we built a little bit more. I wouldn't be able to do demos because how do I show closed source code in a talk? But I'll definitely explain how we build the infrastructure for that. So first of all, one of the good things about having a closed code base, having a mono repo, is that we can have company-wide things. So one thing that I would like to talk about is a company-wide semantic index. So we can take all those semantic DB payloads, which are just case classes in protobuf bindings, and then we can index them. So that's one experiment that we did last year. We took all the information about our source code, all those millions of lines of code, and then put it into an SQLite database. So no fancy distributed key value stores or anything, just an SQLite database. And surprisingly, it was just a few gigabytes. I was like, whoa, this cannot be. What do you mean? You take 10 millions of lines of code, and it's just a couple of gigabytes, and then you can query this with single or double-digit response times? Wow, this cannot be. But well, apparently it is. So just to normalize the results of the experiments that we did on open source code bases, like the community build. So for every million lines of code, you need approximately 500 megabytes in this SQLite format. And then this includes the indexes, which means that queries like find all references go to definition, they become instantaneous, basically. Well, when I'm talking SQLite, these are our open source experiments. Internally at Twitter, we were using a different storage technology, but similar characteristics. Now, there's another cool thing that we've been able to build on top of this company-wide stuff. It's called Companywide language server. So basically, you take the semantic index, and then you expose its data via LSP. So LSP is a great initiative in the sense that lots of editors support it. It's well understood. And so how about we just expose LSP as opposed to a custom relational or whatever database? So our experimental implementation, it just goes to that database and implements just the basic functionality necessary for the basic deliverable. That is text document definition. This is a method in the LSP protocol, like go to definition, and text document references, i.e. find all usages. So that's quite neat to be able at any time to reference semantic information about the entire code base in the company. So I mean, it was a great research problem. It was great to work on it. And what's even better is that it's useful for our customers, that is users of Scala programmers at Twitter. Now let's see how these infrastructural pieces fit together and how they help us achieve experimental solutions to the original goals, why our team was funded in the first place. So first of all, for code browsing, we have an experimental IntelliJ plugin. So it uses this company-wide language server to implement custom go-to definition and find references menu items. You really open IntelliJ. You don't have to open the entire source code, doesn't matter. And then you do a right click, and here we go. You just have a list of references, and it works across the entire code base. Granted, of course, it has been indexed. So definitely there is a research question for future work. How do we make sure that indexes are generated fast enough? How do we make sure that they're synchronized with your local state? For instance, if you're developing locally in a branch. But the current results, they are already much better than the state of the art. And the state of the art is basically textual search. So that's quite neat. Now on to the next thing, code review. I mentioned before that we're using Fabricator, and Fabricator has something called diffusion external symbol source, which is a long-winded way of saying, well, something that can reply to go to definition. So we upgraded this thing, which was supported in PHP and Python. We asked upstream to integrate this into the main product. So now it takes into account source positions. And now that we have source positions and file names, we can just go to our LSP server and ask it for information about symbols. So as a result, in code reviews, if something has been indexed by our index and exposed via language server, we can just use hyperlinks to navigate there. Finally, the final bit, code evolution, i.e. refactorings. Internally, we have integrated ScalaFix into our workflow. It's integrated into Pants, our build tool, and we're basically closely following the cutting-edge milestone builds. Whenever Olaf pushes a new release, we're just immediately jumping on it, which is quite neat. The pace of development and useful features that are coming up recently, they've been amazing. One adjustment that we had to make to ScalaFix, which we're using as is otherwise, is integrating it with our build cluster. As I mentioned before, lots of code. If we were to just build this code with our compiler plugin on our laptops, it just wouldn't finish in reasonable time. So we have integrated ScalaFix into our infrastructure so that you can spawn distributed jobs, like multiple hundreds of thousands of workers, and then obtain a Git diff at the very end. I won't be going into details here to leave time for questions, but there's been a talk by a member of our team, Uma. She's been presenting at Type Level Summit in Boston earlier this year called ScalaFix at Twitter Scale. That provides more information about ScalaFix in general and how we're using it at Twitter. All right, time to wrap up. What we've seen today is that a year ago, we founded the Advanced Scala Tools team, short for AST, with a concrete goal to improve code browsing, code review, and code evolution in our workflow, and also potentially contribute our improvements to the open source if they end up being useful. So as a result, I believe we do have a useful artifact, Semantic DB, which is a data format for semantic information that Olaf and I developed together, thanks to the funding from Twitter and Scala Center. And on top of this infrastructure, internally at Twitter, we have implemented experimental improvements to the areas of interest, which were on our roadmap initially. And these improvements, they use both open source software like ScalaFix and closed source stuff for something that we cannot open source, like our build cluster. Finally, good news. If you're interested by this talk, if you're interested in compilers and just willing to get this done, you can drop me an email. We're hiring and really looking forward to hearing from you. Thanks, guys. Please go ahead. So I guess you'll need to go for the mic, right? OK. Thank you.
So I'm guessing that since you're not running an instance compiler, you're not running the typer either, right? Do you find a lack of typing to be a problem?
Great question. OK, so speaking of the type checker, so indeed we don't have a live type checker, so we cannot type check things on the fly. However, a type checker is involved in this whole process because in order to obtain Semantic DB payloads, we compile stuff with the Semantic DB compiler plugin. So as a result, the type checker happens, then we traverse the results, and we fetch all the information that we can find there, and then we stuff it into Semantic DB, obtaining information like this. So this info comes from the type checker, and this, so because type checker resolves references. And afterwards, after this information is obtained, we store it, and it's available anywhere. So we decouple production and usage of semantic info. And as a result, we gain the ability to scale out. That's an explanation in a nutshell. Hope this answers the question. Thanks. All right. Anything else, guys? Thank you, Martin.
Yeah. First, awesome work. I really think this is amazing what you did for the developers here. The other thing is regarding Taystee. It's true, it's very, very, very early days. So there's one slight difference between what we did in Reflect and what we do in Taystee, which I think is significant, that in this format here, there's no connection between the compiler and this format, whereas in Scala Reflect, the compiler essentially inherits the Scala Reflect APIs. So what that means is that in the future, we can evolve Taystee and the compiler completely independently. So because there is no link. So I think that's important. The other thing is, yes, it needs a compiler instance, but the compiler is structured differently. It doesn't need a global anymore. So it needs just the bits of the compiler that depend on the Taystee, which should be less. But I agree, it's still something that essentially you have to roll in your class path. Yeah, thank you.
Thanks a lot for clarifications. Definitely, Taystee is an improvement upon state of the art, and so once that is released, we're looking forward to playing with it. All right, please approach the mic.
Speaking of, this slide actually in particular, why was the word universe brought into the code base? Where does the word universe come from? I've always been curious.
If Martin doesn't mind, maybe he can answer that. So, okay, fine. Well, so when I came to EPFL, it was summer of 2011. There was already the Scala Reflect project underway. It was based on Gilles Dubochet's thesis, as well as his collaborations with other guys, Martin, other guys in the lab. And so Universe, as far as I understand, it was inherited from there. Back then, in the times when we were using Scala C, where we have a cake pattern, like a huge thing, a global, something that Martin said, that encapsulates everything. I guess this megalomania, it was inherited and reflected in this name, like universe, everything that you can think of. But to be completely precise, we should probably ask Gilles. He's not at the conference, but yeah, that would be a good way to figure out.
Yeah, maybe one. I only can speculate. I forgot what it was exactly. But I think it was because at the time, Java class loader defined a universe. So basically all the classes in the world exist in different instances, once per class loader. So that was sort of alternate universes to define the same object class and to basically have separate versions of all the classes. I think that's where it came from. But I'm not 100% sure anymore.
Great to know. Yeah. It's good that you didn't ask me that at my PhD defense. All right. Anything else, guys?
Time out. Everything else, please take it offline. Thank you.
OK. Well, apparently that was the last question. Thanks, everyone.